When do you pause to have a break when riding a bike? Imagine it's really hilly. So you're in a hilly area, you're going for a ride. You know, it's a very, very big hill. So you're pedaling all the way up the hill, and when you get to the top of the hill, you stop. You are, what's a word? Stationary. Okay? Lines are often used to model real life things like hills. So we have quadratics, we have cubics. They are modeling potentially a hill. Okay? So if we look at a stationary point, a point that's, you stop on your bike, what is the gradient at that point? The rise over run. Not 1, 0. Okay? So the gradient for a quadratic is the turning point. Sorry, the gradient when it's equal to 0 is the turning point of the quadratic. So this is, dy dx equals 0 at this point. Okay, so when you're doing things like finding these stationary points, imagine you're on a bike hopping off, when the gradient becomes 0, this stationary point on the graph, okay? So on a quadratic, how many stationary points does it have? 1. On a cubic, 2. Stationary point. Okay? So sometimes it's a turning point, sometimes it's a point of inflection. So that's what I want to focus on now. Turning points versus points of inflection. Okay? So a turning point, imagine the hill again. You go, the gradient is going uphill, and then the gradient goes downhill. So the graph would look like, if the gradient's going uphill and then it goes downhill, it's an upside down quadratic. It's this phrase, the nature around the stationary point. So if you look either side of the point, it's kind of describing what's happening. So this one, it's got a positive gradient, then 0, then a negative gradient. What about this one? It's got a negative and then 0 and then positive. So that's an example of a turning point. Then we have a point of inflection. So have a read. What do you think a point of inflection is? So there's no uphill, downhill. It's different. They're both greater than 0.
It's like that middle point on the trinomial. It's like, and then it keeps going the same direction.
Perfect. So it goes up, stationary point, and then up again. So it's like, whee, like a roller coaster. Okay, so you're going up, you stop on your bike at the stationary point, and then you keep going up this massive hill. Or they could be both less than 0. What would that look like? Yep, so you're going downhill. I don't know, I guess maybe you would hop off your bike, have a rest from downhill, and then keep going downhill. So negative, 0, negative. A bit of a better diagram of these. So this one is it turning point or inflection? Turning point, and then that's inflection. Okay? So that's the difference. You're looking at the nature around the point. So you would probably like fill out a table or something, like the x values, and then you would say, it's going up and then 0 and then up at certain points on the graph, something like that. So the dy dx, or the rate of change. So this is an inflection table. Or the table tells us it's an inflection graph. Okay? So you can use x-intercepts, y-intercepts, asymptotes, and the stationary points to sketch a graph. So let's do an example of finding the stationary points. The first step, what did I say? Finding the derivative then we find the what? We find the rate of change when it's equal to 0. So if we have the rate of change or the derivative equal to 0, that's when the stationary points appear. So we want to make this equal to 0. We want to find the factors of this. So first divide by 3. Alright, and then we're left with x take 6 and x plus 1. So x is equal to 6 and x is equal to -1. So this is the location of our stationary points, or the points where we're hopping off the bike on the hill. Okay? So now what do we do? Sub them into the original function. That gives us the y values, and that's the stationary points. So I'm subbing in x equals 6. So I found the stationary points on this cubic. You notice there's 2 because it's a cubic. And you finish with the sentence answer of where the stationary points are.